So this is drilling flow training produced by me, Amr Ibrahim. Thanks for OPA for their efforts. Okay, so I will start with my biography. As I told you, I graduated from the Petroleum and Faculty of Petroleum and Mining Engineering, Suez University at 2011. I'm working as a drilling fluid engineer since 2011 till now, and I am accredited instructor and assessor of ADAM-CF and Well Sharp service BOB. Okay, so now we are going to start with our quick rig familiarization. As I told you, it's very important for you guys, especially that I know that most of you are still students, so it's important to introduce with this introduction about rig familiarization. So just a minute. So I will talk about the land rig, not the offshore rig. You know, offshore rig is somehow different, but what I need for illustration will be enough as a land rig. So this is a scheme of normal land rig. So we will highlight some important parts that will be required for us to understand the drilling flow training. So as you see here, there is a caravans of the managers, you know, cameraman, tool pusher, my caravan, mod engineer, lab, and all the office at the site. Here, you know, this is the rig mast. You know, the biggest part of the rig. You can see it from very far away. The rig mast contains a hoisting system, which is responsible for lowering and lifting the pipes. So here you will find the crown block, and here you will find the traveling block, and in between you will find the drilling rope or the drilling line. This line are responsible for go up and go down using this small, you know, this blue. It's called drum. This is have the rope of or the line of the drilling line. So the driller can use the brake to go up and go down using this line and traveling block. This crown block is fixed on top of the mast, so that the line is going through it using the traveling block. Here you see the top drive, and top drive is very important. And you know, it's maybe 15 years ago or 20 years ago, we are not using this top drive, but we were using Kelly, and it still be used till today, but very rare now, because top drive is very powerful tool. We can use it to make a connection for 3 joints, not only 1 joint. At the Kelly operation, we were using only 1 joint, so it will take time to make a connection. So with top drive, we can make a connection of 3 joints, which is around 30 meters or 90 feet. And the drilling is faster than the Kelly operation. Also here, this area is called the rig floor. And you know, rig floor is the most important part of the rig. Here, everything is happening here. You will find this one is the dog house or the driller cabin. Guys, you know that this industry started at USA, so, and you know, they are fond of animals. So you will find a lot of names named after animals. So you will find dog house, you will find something called catwalk, mouse hole, so monkey port. So don't disturb yourself with these names, just named after some animals, because this industry started at USA. At the mast, you will find the monkey board or the Derrickman board. This board, the Derrickman working on it while connection time or while tripping time. when the stand go up with the top drive, he pulls the stand and put it in the fingers here of this board to rack back the stand. Okay, also you will find here, this number 7 here is the mouse hole. The mouse hole, it will be clear in another view. Okay, this is the mouse hole. What is the importance of the mouse hole? The point, the mouse hole is a small, is a pipe extended from the rig floor to close to the cellar area. We can use this to put the joints that are going to make a connection, or any small bob joints. So it is just a reserve for the joints to be next used on the top drive. Also, we'll find here the catwalk. The catwalk, we put the pipes here, and it's go to the V door to go to the rig floor through this inclined V door. Okay, the most important part for us now is this part, is the mud system. Starting the mud system with this mud gas separator. It's used when we are facing high gas content of the mud. So we direct the flow to the mud gas separator, then to the shakers. You see here, this is the flow line. This is the flow line. This is the flow line. Guys, okay, I will respond to this question. What is the importance of mud gas separator? I just said that the mud gas separator is used to separate the gas when we have a high gas content on the mud. You know, there is a difference between the mud gas separator and the mud degasser. The mud gas separator is used before the shakers, and this is used because if we have a lot of gas or high gas content on the mud, so we cannot enter the mud to the shaker area with this high gas content. So we direct the flow to the mud gas separator to separate the gas, and this gas could go to the flare line. But the mud gas separator used when we have a minimum or a small amount of gas. And we know this amount of gas through the mud loggers. Okay, so this is a choke manifold through a mud gas separator. Then this is our tanks. Start with the mud, the sand trap and shell shaker, then the descender, desilter, mud cleaner, then mud gas separator, mud degasser, and then our tanks. And here you can see the mixing area. Here you can see from this view the tanks, and you will find the rig pump. Okay, you will find the waste pit, which is just below the shaker area, so that we can receive the cutting on this area. Okay. Also from this view, you will see the BOP. It's here. The BOP is the blowout preventer, and this is the second barrier for if we have any kick situation or blowout. Kick. If we have any kick, so we will close the well using the BOP to avoid any further action like blowout or something like this. When we are going to start with our drilling fluid functions, you will find that the first function and the most important function is to provide the pressure control for the well. So if we lose this pressure control, if we lose our primary barrier, so we have to close the well with a secondary barrier so that we can control the well. You see here our mixing area. And this mixing area, we have it is a chemical area. This chemical area has, we can store our chemicals so that we can later on bring it to the mixing area or hover area to be used for mixing. So you see here, this big silos, it contains the barite or bentonite, and it is not common in all rigs, but you may find it in some rigs. Here, this tank is considered to be the mixing tank, but it's not like this because, maybe we use normal tanks for mixing or this tanks, whatever. You see here, it's not important to describe, but just the generators that deliver the power for all the rig. I think that's all the important part to start our session with the drilling fluid. I just want from this session to just describe a little bit about the drilling rig for anyone who didn't visit a rig before. So I will allow for 5 minutes for questions before starting our main session, which is the drilling fluid and drilling fluid functions. So guys, please write your questions on the chat and don't overload me so that I can answer the questions. Maximum 5 to 10 questions. So let's go. Okay, it is not POP, it is BOP, which is a blowout preventer. Blowout preventer here, we can see it again. This is the blowout preventer. It is I will speak a little bit with in Arabic, guys, so that maybe my friend will understand. It's a blowout preventer. It is used ده بنسميه البي او بي اللي هو البلوwout بريفنتور. ده بستخدمه امتى؟ انا دلوقتي عندي البير بحفره، ولما نيجي نتكلم عن اول فانكشن من الدريلنج فلويد اللي هي الفانكشن بتاعت البريشر كنترول. انا بحفر سي ان انا مثلا في بريشر هنتكلم عنها كمان 10 دقائق بالكتير، لكن سريعا كده ان انا ببروفايد ماد ويت انف ان هو يمنتين البور بريشر عشان ما يحصليش اي كيك. فنفترض ان انا يعني خسرت البرايمري كنترول دوت، او خسرت وزن الطفله لاي سبب. حصل لي مثلا دخل ميه بشكل غلط على الطفله، دخل جاز من الفورميشن، اي سبب خلى الوزن الطفله يقل، فقدت البريشر كنترول. فلما فقدت البريشر كنترول، طب هعمل ايه؟ كده ممكن لو فقدت البريشر كنترول وحصل uncontrolled فلو من الفورميشن، فكده ده اسمه الكيك. ولو الكيك ده انا سبته وما سيطرتش عليه هيحصل لي بلو اوت. فبيبقى عندي السكندري بارير. طبعا الكلام ده بيبقى مشروح اكتر طبعا في الويل كنترول، لكن خلينا نتكلم بشكل بسيط. السكندري بارير دوت اللي هو البي او بي ده بيكون ميكانيكال ديفايس، بيكون عباره عن اكتر من حاجه كده اسمها الانر بريفنتر، وبعد كده الرام. من الاخر يعني انا بقفل بيه على المواسير، بقفل البير بشكل ميكانيكال عشان خاطر امنع اي تدفق غير متحكم فيه من البير. اوكي، دي كده ايه بشكل سريع موضوع البي او بي. اوكي guys, I just the guys who asked me to continue in English, I just described this POB on Arabic so that my friend can understand it. So it's clear now. Okay, so no more questions. Number 14. Where is number 14? Okay, this number 14 is called the COMI unit or accumulator unit. We can describe it simply as it is the switch of the BOB. You know, this BOB is a very big device and need high pressure to close and open. So there is a lines connected between the BOB and this COMI unit, and there is like a pressure storage in the nitrogen bottles. We can use it in case of any failure of power. We can run the BOB with mechanical pump, with electrical pump, and in case of the failure, we can use this nitrogen bottles. So this is a COMI unit is we can describe it simply as it is the switch of the BOB. Okay, we can open, close any part of the BOB from this COMI unit. Okay. Okay. Two white containers. What inside them? I said this already. This okay. This silo. This called the barite and the bentonite silo, or we can call them the bulk silo. We can call them the bulk silo. Why bulk silo? Because you know we are using a lot of barite and bentonite, especially. You know, barite is used for weighting as a weighting material, and the bentonite is used as a viscosifying agent. So we are using a big quantity of this. So we have two ways to bring them in big bags. Every one is 1 metric ton, or for the barite 1.5 metric ton. Or simply we can use this silo. We can bring the barite or bentonite on trucks and fill the silo with barite, bentonite, and we can use them easily instead of big bags. So this is alternative way, but as I told you, it is not common. You will not find a lot when you go to the rigs, but some rigs use this silo, okay, bulk silo. Okay, what else, guys? Any other questions? Okay, do you think the degasser is able to remove H2S? Okay, the degasser can remove the gases, but you know there is a limitation. But 100% we are using it to remove any type of gas. So we can use when we have any amount of or any gas, any high amount of gas. So usually we use it. We use the mud gas simulator at least to divert this gas to the flare line. Okay, but you know that H2S, there is different measurement for H2S, and if we cannot control it, so there is a protocol for every company man that in case there is no control for H2S, so he has to fire the rig. And maybe some of you will find this very strange, but I didn't see it myself. But there is a story for a very famous company man at KSA. He saved a lot of lives by firing a rig has uncontrolled H2S, and he is honored by Aramco, and it is a very famous story. So if we cannot control H2S, so the company man has the authority to fire the rig, and he has this firing guns at his office, and he can use it when he finds he must to do it. So what else, guys? Okay. Okay, so I see a lot of message about H2S, and the guys are replying to each other. So it's good that we help each other to deliver the message. Okay, Jeffy is saying that the first barrier is the drilling fluid. Okay, this is the first barrier already, and in case there is any failure of this first barrier, we use the secondary barrier, which is BOB. Okay, guys. Okay, so guys, please, it's enough now with the questions, so we can continue with our main session, which is the function of the drilling fluid. Okay, so the drilling fluid, this is a big agenda, but we are not, with a time limit, we are not going to use to describe all the function. We will describe the pressure control, hole cleaning, suspend solids, and minimize formation damage. And in case we have some time, we will talk about briefly on the maintain well bore stability. Okay. So before starting with this drilling fluid function, I see this similarity is very good to start with, to describe how important is the drilling fluid. The drilling fluid is very important to the well, and for you to sense this importance, let's describe this similarity between the human blood and the drilling fluid. Okay, this column for the human blood and this column for the drilling fluid. You know that the human blood is responsible for eliminating any waste product of our metabolism, and we have a lot of organs that is responsible for this cleaning or elimination, like liver. In the draining fluid, you know, it's used for hole cleaning, to remove the cutting from the hole. And if we didn't remove this cutting, so we actually didn't drill. Just we make the cutting friable. And also our blood is used to equalize our our body temperature. If we are in a cold place, so our blood help us to warm a little bit. If we are in a warm place, so our blood help us to cool a little bit. And the draining fluid help to cool and lubricate the drill bits and soften the rock. With the human blood, it is used. The circulation happen by the heart, okay, through the system, the artery vein and connection of our body. And also for the draining fluid, we are using the triplex pump of the rig to pump it through the drill string to the annulus back to surface. Also, the human blood is reusable. As we said, the blood is eliminated from its waste using the elimination organs. Then it is reusable again. Also, our drilling fluid is the same. We clean it from the cuttings using solid control equipment, and it is reusable again. Also, our blood contains white blood cells, red blood cells, and some enzymes to help it to do its job. And also our drilling fluid contains some additive to help it to do its job, like viscosifiers, weighting material, formation damage prevention material. So there is a similarity, very good similarity, to sense the importance, how important the drilling fluid. And I see it is very interesting similarity, because no one will doubt the importance of our blood in our body. So that if you feel this importance, so you will reflect this importance to the drilling fluid into the well. Okay, so let's start with the most important. Okay, I see some messages here. Okay, so let's start with the most important, and I will take a lot of time in this function, because it is very important. And if you understand it, so you may understand anything in the drilling fluid functions, because this is the most important and the most critical function of the drilling fluid. Now, as I told you in the rig familiarization, we have to maintain our pore pressure. Okay, so what is the pore pressure and what it is depend on? Okay, what is the pore pressure? You know that, guys, the fluid, our fluid or our gas or whatever, or oil, it is not down there like a pool of oil. No, it's being inside the rocks. And you know, the spaces between the rocks contain this oil or gas. So if we have a formation, and this formation, there is overlaying rocks. If we have a formation at, for example, 3,000 feet or 3,000 meters, so there is overlaying rocks from 0 depths to this depth to 3,000 feet or 3,000 meters. So this overlaying rock will determine the pore pressure, and the pore pressure will be the pressure of the fluid of these rocks. So let's make a very simple example of this pore pressure. If you have any balloon and you make a hole in this balloon, everyone knows that the pressure inside the balloon is higher than the pressure outside. So if you make any hole inside the balloon, so it will make like burst. So But in case if you make this hole and you put your finger above this hole, so very simple, you will not have any consequences of this. Why? Because you applied higher pressure than the pressure inside the balloon, so you are not going to have any consequence effect or any bad effect. In the rocks, these rocks have high pressure. Why? Because of the density of the overlaying rocks and because of the tectonic activity. Tectonic activity, the guys who studied geology will understand this very quickly. Okay, guys, as I told you, please try to make it the chat just for questions. And at the time, I told you to start writing your chat because you know this chat still coming up and make disturbance for everyone. So please, we need to help each other to deliver our message. So guys, we are talking about now a formation that have rocks, and there is interstitial fluid inside these rocks. The fluid which is surrounding the rocks, which is inside the spaces of these rocks. This fluid has pressure. Why? Because the overburden pressure, the density of the overlaying rocks. And there is also a tectonic activity. Tectonic activity, for example, the guys who know the folding and the faulting, from where this come from the movement of the platelets of the earth, which make like compression and tension, which create the folding and the faulting, which affect the pore pressure of the formation. And also, there is a point of if the rocks itself is supporting or supported by the fluid. As I told you, there is a fluid inside these rocks. And this rocks is maybe okay. Now we are going to describe one of the most important concepts in the oil field. Guys, when I talk about the pressure control function of the drilling fluid, you will find me all the time said that it is the most important thing. Here, it is the most important function. And this mud window is the most important concept. And when we are talking about the hydrostatic pressure equation, it will be the most important equation of the oil field at all. Because you know, it is the start. If we cannot control the pressure of the well, we cannot make anything else. We cannot continue drilling. We may lose the personnel, and this is the most important. We may lose equipment. We may lose the well itself. We may lose production. And you know, the recent accident at 2010 at Gulf of Mexico is a very powerful witness of what I'm talking about. So the most important concept is the mud window. What is the mud window? I told you that there is a formation pressure or pore pressure. We have to control it. We have to use hydrostatic pressure, and later on we will describe why we are saying hydrostatic. The concept hydrostatic is the pressure that comes from this column of mud and the static condition. For example, a very simple example, if you have a bottle of water and an empty bottle, and you put it in a scale, for sure you will find the bottle of water has higher weight. Why? Because this mud column or this water column make a pressure on this area, make a force in this area, so it is a pressure. So the hydrostatic pressure is the static pressure. So in the static condition, we have to use hydrostatic pressure of the mud higher than the formation pressure. which is the pore pressure. Why we call it pore pressure? Because I just told you that the fluid, the gas or oil or even water, it is inside the porous spaces between the rocks. So we named it the pore pressure or formation pressure. But there is a limit. Guys, when we are talking about drilling fluid, and we said any parameter of drilling fluid, mud weight, viscosity, fluid control or fluid loss, when we are talking about any parameter, there is limit for every parameter. There is minimum limit and maximum limit. When we said that we have to overbalance, we have to increase our hydrostatic pressure to be more than the formation pressure. Okay, for example, if we have formation pressure 3000 psi, so we can use 3500 psi as a hydrostatic pressure. We can use 4000, we can use 5000. What is my limit? So my limit is the fracture pressure. What is the fracture pressure? The fracture pressure is the pressure at which the formation will break down. Guys, now we have a formation. This formation has two parameters. I cannot control these two parameters. This is given information from the formation. This is given information. So the formation pressure and the fracture pressure, it is from the formation. I cannot control them, but I can handle them, but with my hydrostatic pressure through the mud window concept, that my hydrostatic pressure and the static condition should be higher than the formation pressure, but lower than the fracture pressure. Okay, let's see if we are not following this mud window, what we are going to have. So this BF is the formation pressure. If our hydrostatic pressure is much greater than the formation pressure, that go close to the fracture pressure, so maybe I have loss of circulation, maybe I break down already the formation and lost the draining fluid. Maybe I have hole instability, and this will be described later on, but just as a brief, we will have hole instability because of, there is some formations like shale formation and like depleted formations that will be affected by this high pressure. Also stuck pipe, and especially the differential stuck pipe. When we push the string too much against a permeable formation, so we will have a stuck pipe. In case if we use hydrostatic pressure less than the formation pressure, as we said in the introduction, we will have influx from the formation fluid into the wellbore. And the point is, it will be uncontrolled influx. Guys, when we finish drilling and put the well into the production phase, so we let the fluid to come out for the production. But now, while drilling, we cannot let the fluid to come out. It will be uncontrolled influx from the formation. And this is exactly the definition of the kick. And if we have a kick, so we will have a well-controlled situation. We have to close the well, we have to kill the well, and if we lose this control with the BOB, maybe we have a blowout. That's why I told you this pressure control is the most critical and the most important function of the drilling fluid. Okay, guys. So I told you that we have mud window. We have to use hydrostatic pressure higher than the formation pressure, but lower than the fracture pressure. But what is the field usage of this concept? We use something called the trip margin. We use around, as a rule of thumb, from 100 to 200 psi as the overbalance. What is the meaning of overbalance? Let's say, for example, that we have a formation pressure of 3000 psi. If we use a drilling fluid with a certain mud weight at a certain true vertical depth, so that this fluid give me 3000 psi, in this case, I will say that I am balancing, just balancing. The formation pressure is 3000 and the hydrostatic pressure is 3000. Overbalance is to use a mud column with hydrostatic pressure more than the formation pressure. And usually we use this overbalance margin 100 to 200 psi, which is called trip margin or safe margin. There is a cases that we use underbalance drilling, but this is a different cases. It is not the scope of this session, so we are not going to talk about it. But the normal is we are using the overbalance of 100 to 200 psi trip margin, okay, as a safeguard against any well kick. Okay, guys. So now we are going to talk about the equation. And as I told you, it is the most important equation for the oil field. It is the equation that calculates the hydrostatic pressure of the mud. Okay, guys, when you see this equation, anyone may think that it is 4 equation. No, it is not 4 equation. It is only 1 equation. But you will find that there is a difference in the units, because maybe in different countries use different unit sets. But the most common one is this one, the third one, the hydrostatic pressure with psi, which is pound per square inch, equal to 0.052 multiplied by mud weight with the unit of ppg, which is pound per gallon, multiplied by the depth, which is the TVD, true vertical depth, of feet unit. If you are going to use any different sets, for example, gram per cubic centimeter and meter here, so the constant will be different. And guys, this equation is, this number come from just conversion numbers. For example, this psi pound per square inch, but this is pound per gallon, and here is feet. So we will transfer or convert the gallon to feet cube. Then the feet square will go to inch square. So this 0.052 or 0.433 is just conversion constant. Okay. So the point is, the point is that the hydrostatic pressure is equal to the constant multiplied by the mud weight or the mud density with any unit, multiplied by the depth, which is the TVD. What is the TVD? The TVD is the vertical distance between the surface or the well origin point to the point I'm going to calculate on it. You know that this mud is going through this string and go to the annulus, and all of this is filled with mud column. So if I'm going to calculate the hydrostatic pressure at this point, so I will multiply, for example, using this equation 0.052 with the mud weight with ppg, let's say 12 ppg multiplied by the depth, which is, for example, 10,000 feet. So I will have the hydrostatic pressure. Okay. Okay, guys. So now we are going to talk about what now? Okay, one guys okay, did you ever need to calculate something while working in the field? Yes, yes, of course. I will talk about my job. While we are mixing, it is my responsibility to provide the mixing recipe. So I have to calculate the mixing recipe. But for the pressure and the mud weight, and as I told you, it is the most important thing, and it is the pressure control. So we get this from the drilling company or from the company that has the well itself. We call it the operating company. The operating company. They provide the mud weight calculation and pore pressure calculation for us in the drilling program. And guys, increasing the mud weight or decreasing the mud weight is not that easy on the field. To increase the mud weight or decrease it, it takes too much time to decide. And as a mud engineer, it is not my decision. My decision is based on the treatment of the mud. But because the pressure control, as I told you, is very critical, so it is a big decision come from the top management of the operating company. It is not that easy. Okay, guys. Now we are going to talk about a very critical concept in this point, which is the ECD, which is equivalent circulating density. Guys, you remember when I talk about the hydrostatic pressure? Hydrostatic pressure, all the time, I said hydrostatic pressure. But did you think that the mud will still hydrostatic or static while drilling? It's not make sense. Doesn't make sense, right? So the mud will circulate. The mud will be circulated using the pump to elevate the cutting. At least, just to clarify this point, we need to circulate the mud just to take the cutting out of the well. There is a lot of reasons to circulate the mud, but just say for illustration this one. So the mud will not stay static. The mud will move, will be dynamic. So guys, let's think about this. When we start circulating, pumping the mud from the mud pump, as we see in the familiarization, it will go through the service line, then go to the drill string, okay? It will go down, down, down until go to the drill pit, then go out through the annulus. And when I'm talking about the annulus, just it is the annular space between the drill string. Guys, try to imagine that this well is circular, not like this, just a section of the well. But this well is circular and this drill string is circular. So the space between these two circular, the well and the drill string is called the annulus. Okay, guys. When we are pumping the mud, so we use a mud pump with certain pumping pressure. This pumping pressure is lost during the whole journey of the mud from service back to service, where this pressure is lost. Guys, I'm talking here about the pumping pressure, the pump pressure. Okay, we lost this pressure through all well component. We lost this pressure through all well component, starting from the service line, then the internal of the drill string with different size, then add the bit itself, okay? Then we lose some pressure, pumping pressure at the bit itself. Then we lose some pressure in the annulus and this is the most important, that what I'm describing this to get this point, to get to this point. The annulus pressure loss or annular pressure loss. The annular pressure loss is the pressure which is lost, the pressure lost from the pumping pressure to the annulus. And think about it. When we are circulating, where we can sense this lost pressure in of the annulus. If we put a pressure gauge here at the bottom of the well while circulation, we will sense a higher pressure while circulation or lower pressure. Guys, think about it, because it is somehow difficult to be imagined. But if we imagine it like this, that you put a pressure gauge here at the bottom of the well. The bottom of the well at the static condition just sense the weight of the mud column here at the static condition. But what about while dynamic condition? There is a pressure loss here at the annulus due to the friction. So when we put here a pressure gauge at the bottom, we will sense a higher pressure at the bottom. This higher pressure while dynamic condition is affecting the formation, affecting the bottom hole pressure. And when we are talking about the bottom hole pressure, it is the summation. It is the summation of all pressure affecting the bottom hole. For example, at the well control situation, when we close the well, we will have like shut-in casing pressure and shut-in drill pipe pressure. So when we are calculating the bottom hole pressure, we will consider this closing pressures. So anything affecting the bottom hole, it is the pressure above or the summation of any pressure affecting the bottom hole. This is the bottom hole pressure. So in the case of dynamic condition, if we put a pressure gauge here in this area, so it will sense a higher pressure due to the friction at the annulus. Okay, this is translated to the ECD, the equivalent circulating density, which is reflecting the increase of pressure sensed by the formation at the bottom. So this pressure, how can we calculate this annular pressure loss? We can calculate it by the BWD, tool. BWD tool. We can use the BWD tool to describe this or to measure this pressure. Okay, so if we are going to calculate the ECD, the equivalent circulating density, it will be what? It will be the original density, the mud weight density, the original mud weight density plus the annular pressure loss, which we measured it using the BWD tool, divided by the depth and the conversion factor, which is in this case 0.052. So just we will convert this annular pressure loss, which is measured by the BWD tool, to density, then we will add it to the original density so that we can calculate the ECD, the equivalent circulating density. So guys, we will take 5 minutes for the questions before starting with details at the pore pressure and fracture pressure. So let's check what we have here. Okay, there is a difference between the LWD. LWD is the logging while drilling. LWD is logging while drilling, okay? But BWD is pressure while drilling. You know, LWD is very common. Sorry guys. Yeah, LWD is logging while drilling. BWD is the pressure while drilling, and MWD is MWD is a measurement while drilling. So the BWD tool is a tool installed by the same crew of the MWD or directional guys. And this tool is used mainly to calculate the ECD. And we use it especially when we are in a situation which is narrow window. Guys, narrow window. Narrow window. What is a narrow window concept? I talked to you about the mud window. For example, if we have 3000 psi pore pressure and we have 3200 psi fracture pressure, so this is a narrow window. The problem of the narrow window is that when we say for example we use hydrostatic pressure to be higher than the pore pressure and lower than the fracture pressure. Say for example we use 3100 psi, which is in between. So this pressure good and the static condition. But say for example we have APL of 150 psi. APL stands for annular pressure loss. Okay, so we will have at the dynamic condition, we will have 3250 psi. This will be at the dynamic condition. Okay, so in this case we are exceeding the fracture pressure. So we have to lower our hydrostatic pressure so that I cannot exceed the fracture pressure, or I can decrease the APL as much as I can by what? By introducing by reducing the amount of cutting which is affect the APL, cleaning the well from the cutting, and this will be talked at the whole cleaning function. Okay, what we have, do we have any other questions? Guys, if anyone write a question before, I cannot catch it, so it's time for you to write your questions. Okay, this is a good question. The TVD is measured by the MWD. You know, the DVD, you remember when we talk about the drum that has the wire at the drilling line. When we start drilling, we make the pit at 0 point, and we make measurements or make like adjustment at the 0. Okay, so when the drilling line go down, so we can calculate the TVD. Plus the guys of the logging guys also make their sensor at this drum to verify the TVD, and there is a correction between the driller and the LWD, the mud logger guys. Plus, when the MWD guys came to the rig, they put their sensor also, and they make all of them like correction or same measurement to have the same TVD. So TVD is not measured by anyone. Okay. So it is not measured by anyone. It is just sensors, and we use the drilling line to help calculating this TVD. The measure depth is oh, I'm sorry guys. The TVD, he asked about the TVD. Yeah, the measure depth is used, as I told. The measure depth is the length of the connection itself. But the TVD, yes, it is used. It's calculated by the MWD using the inclination and azimuth data. Okay, so we get it from the MWD guys. So I just confused between the TVD and MWD. But MWD, as I said, but the TVD is calculated by the MWD tools. Okay. Okay, we have to continue. Okay, APL guys, APL is the annular pressure loss. I talked annular pressure loss. Okay, APL is annular pressure loss. Okay, guys. So we will continue. Guys, here I talk about the formation pressure and we talk about the fracture pressure, and now the time is to talk deeply on these two concepts. So the pore pressure, as I told you, it is a function of the overlaying rocks weight. So it makes sense that when we go down, we have to the pore pressure will increase. So the pore pressure is calculated worldwide, and a lot of data gathered from a lot of wells from the worldwide. So we get a worldwide trend of the pore pressure, which is the normal pressure gradient is 0.465. This is from a lot of data. Okay, so let's see this one to understand the effects of the overburden pressure. Guys, here this overburden pressure, when we have a formation like this, there is a fluid inside. This is a simulation of the rocks and the fluid inside. This is a fluid inside, and this is the rock grains. And this rock grains, there is here like a valve we can open and close. So if we make a force from the top, which is representing the overburden pressure, which is representing a new layer, is make sediment here or deposited here. So it will apply a pressure in this area. So if we are closing this valve, what is the meaning of closing this valve? So there is no communication from this formation to the surface. The water or the fluid will not come out due to this high pressure. So the pore pressure will increase as shown here. But in case we open this valve and there is a communication between the formation to the surface, so the fluid will come out and it will be like a compaction process, and the pore pressure is still the same. And the overburden pressure here is equal to the pressure of the formation, the sigma here, which is the stress in the spring, which is in the rock itself, plus the pressure of the fluid. Okay. Why this concept is important to describe this one? This one is very important to be understood. Why? I think most of you heard about the sand lens concept or the shallow gas concept. Why these concepts are very important? Because if we have a formation with there is no communication between it to the surface. So if we don't have any communication to the surface, so we will, if we have any compression, as in this equation or in this scheme, so the pressure will not, the pressure will increase and the fluid will not escape. Here, for example, if we apply any pressure to this formation, so the water will escape, okay? And this sand formation, there is communication to the surface. But let's imagine that we have sand lens here or a formation here, and it is enclosed. I am applying pressure to it, but the fluid is not going out, will not escape. What is the problem of this? The problem is this pressure will hold its pore pressure, and in case I found this pressure in wrong position, I may have a problem. Let's see with numbers. This formation, if this formation have 1860 psi, okay, and if I found it at 4,000 feet, so I will multiply the pore pressure gradient by this 4,000 feet. I will find the pressure the same, 1860 psi. Okay, this will not be a problem. Why? Because I met this formation at good place. But the problem here, if I'm drilling now and my depth is 2,500 feet, if I calculate my pressure with the normal pore pressure, so I will find it 1160 psi. This is the formation pressure, guys, the formation pressure. So if I'm calculating my formation pressure here to be 1160 psi, so it is very logic to use, as we said, 100, 200 psi safety margin. So I will use, for example, 1300 psi. But the problem is I will find this formation with 1860 psi. So definitely I will have a kick. Why? Because this formation pressure is higher than expected. Because this lens or sand lens, I met it in a position that is not expected. Here, for example, for third example, if I made this formation in deeper, so if I'm drilling at 5,000 feet and I calculated my pore pressure using the normal pressure gradient, I will find it 2,325 psi. But the pore pressure at this area, because of this sand lens, is not connected to the surface. It is 1860 psi. So now I am overbalancing, it's okay, but maybe I overbalance to the fracture pressure so I can frag this formation. So guys, I think now you understand how important is the pore pressure data. And if we face any situation that it is not expected, so it will be very, very difficult if we are not using the proper situation to handle it. Okay. Okay. The fracture pressure, I talked to you about it. It is the pressure where I will break down the formation. And there is a lot of details regarding the fracture pressure in this slide, but it is not our scope. The vertical stress, the minimum horizontal, maximum horizontal, it will take too much time to describe. So I will be satisfied with the concept of the fracture pressure, which is the pressure at which the formation will crack. And we calculated how we are going to calculate it when we are drilling for the first time in any area, exploration area. So we use the LOT, which is the leak of test, to calculate it, which we are using the cement unit, close the well, pump a little bit, quarter barrel, and see the pressure response. The pressure will increase till a point it will be start to decrease. So at this point, at this turning point, the formation start already to crack, and this is the LOT, the leak of test. So this is how we calculate the formation pressure. Okay, guys, now we already finished the first and most important function of a drilling fluid, which is the pressure control. Okay, 2-3 minutes just for questions. If anyone have anything, I just need to speed up a little bit so that we have around 30 minutes remaining for the remaining functions. It will be enough, inshallah. So, okay. So, no one have any questions, guys? There is a question: how can we handle this kind of case? You mean what? What's this? What's the case? Nizar, your question is not clear enough, please. What's the case? If we have the overpressure. Okay. If it is exploration well, we called it wildcat well. Why? Because we don't know what we are going to have. So in the exploration well or wildcat well, we have to install the diverter, which is used before installing the BOB. And in case we have this shallow gas or sand lens and there is a kick or uncontrolled fluid flow, so we have to divert it away. And in case we are already using the BOB, so we have to close the well and calculate the kill mud weight and use higher mud weight, because if we didn't do this, we cannot continue drilling. So we have to increase the mud weight to face this overpressure. Okay. How will the well explode if mud enters the fracture? If we lost the fluid, you know, I talk about the fluid column, which is start from the 0 point to the depths of our well. And using this mud column, we reached the good overbalance, which maintains the pore pressure. In case we lost some of this mud column, for example, if we lost 1,000 feet of our mud, so we lost our pressure. So maybe we go under balance and there is a kick. So maybe the well will kick, and if we didn't control it, the well will explode. Guys, don't use the term of well explosion or the well will be explode. No. There is a situation called a kick, which is the uncontrolled, which is the sign or uncontrolled flow of the well. And if we cannot control it, so it will be a blowout or explosion. But when we have any sign, we have the BOB and we will close the well to control it. Okay. Zainab is saying that this course is really hard for geoscience student. Can you suggest any article, please? Right now, maybe I will provide something to OBA team and they will send it to you, Zainab. But I didn't think it is this hard for you because you know you already, as a geoscience student, you already know the formation and how the pore pressure and formation pressure. Just what is missing for you is the hydrostatic pressure calculation, and this is very it's not that hard. And if you don't visit a rig before, so you already see with us the rig. So I think if you listen to this recording again, it will not be that difficult. And there is a lot of articles. Maybe I will provide something to the guys to share it with you. Okay, guys, we will enough with questions here. Okay. Okay, guys. So we will have the second function of drilling fluid, which is the hole cleaning. Okay, guys, hole cleaning is very important, as I said in the introduction. Why? Because if I am drilling a well and there is no removing of the cutting, so I am not actually drilling. I'm just removing the cutting. I'm just make the cutting friable. I just make the cutting friable or unconsolidated. So cutting removal is essential part of the drilling fluid function. So guys, let's see here. So the cutting removal is a function of what? Guys, here you will see, as we said before, the mud come from the rig pump down to the pit and up to the annulus. Okay, this mud is pumped with a certain pump rate or flow rate. This flow rate is pumped through annular volume or annular space. We talk about it, the space between the hole, circular hole, and circular drill string. Okay, this annular volume, when we divide the pump rate over the annular volume, we get the annular velocity, which is a key factor in the cutting removal. The annular velocity is used to remove the cutting from the well, from the bottom of the well. The annular velocity is the velocity of the fluid, of the mud at the annulus. And we can calculate it using the flow rate divided by the annular volume. We will see its equation later on. Okay, guys, here when we concentrate in this one, you will have that the cutting, we can see it here. This cutting has a sliding tendency to the bottom. Why? Because of the gravity. So you can see here the red arrow, the cutting want to go down by the gravity, which is the slip velocity. And this is the annular velocity going up. So there is two forces here, the annular velocity and the slip velocity. In the vertical section, it is very simple. We make good flow rate, make higher annular velocity to overcome the slip velocity to avoid this cutting to go down, and we will achieve the required hole cleaning. So the annular velocity factor is very essential factor. It's very important factor in the cutting removal. Okay, guys, what else will be a factor of the cutting removal? The cutting size, shape, and density. You know, guys, especially guys who study geoscience, there is a lot of formation type. We have shale formation, sandstone, we have limestone, we have a lot of formation, anhydrite, gypsum. So all of this formation has different cutting size, different shape, different density. So this is an important factor in the hole cleaning. By logic, if the cutting size increase and density of this cutting increase, so it will be hard to be cleaned. What else, guys, as a factor of the cutting removal? The viscosity. And guys, when we talk about the hole cleaning, usually we use two terms together, which is annular velocity and viscosity. So when in the case that we cannot provide the required amount of annular velocity, I have a limitation with the pump pressure. I am drilling a big section or a top section, which is, for example, 22-inch hole or 17.5-inch hole. So this section I cannot. There is a limitation for the annular velocity, and also the annular volume is big enough that the annular velocity is decreased. So the viscosity will play the big role in this situation. We have to increase the viscosity enough to help cutting removal. For example, guys, any guys go to the rig or read about drilling operation, we use as a service section the mud called spud mud. And this mud is just bentonite, mud and water and bentonite to provide the required viscosity to help cleaning the well. Okay, guys, what else is a factor of cutting removal? Is the ROB, number 4. And guys, ROB is important in this case. Why? Because I cannot fill the annulus with cutting to a certain limit, and I said that to myself, hey, annular velocity is good, viscosity is good, it will be clean. No, guys. ROB is very critical factor in this cutting removal. And I have a field experience in this ROB case. One time we were drilling in a surface formation, 17.5-inch hole, and the surface formation, usually the formation is easily to be drilled. And we have a high ROB, and we have to control it. The driller have to control the ROB. And I don't know why the driller make a mistake or just have bad instruction or what. He drilled two full stands, two stands with an instantaneous ROB of 120 meter per hour. And guys, this is a very, very high number. This is very high number. This is very high ROB. The result of this, that the flow line plugged, all the well is plugged and we cannot continue. And if we try to bump, the pressure, the moment pressure is going up, and it was like a mess. It's this very unforgettable day. So in this situation, when we make a calculation, we find that the cutting load in the annulus is around 10%. And 10% is too much. You know, as a rule of thumb, you cannot load the annulus with more than 3% of cutting, or you will have a bad hole cleaning. What is this 3%? The 3% is by volume. For example, if the annulus volume is 100 barrel, so the maximum amount of cutting you should have in the annulus is 3 barrel. Okay, so in this situation, we have like 10% of the cutting inside the annulus, and it is catastrophic event. But fortunately, the mud viscosity was good, so that we try to regain circulation a little bit. And you can't imagine how big cutting we got from this well. Bit like cutting like the size of stabilizer. So ROB is very important, guys. Okay, number 5, the drill string rotation, the RPM. You know that we are using the drilling, we rotate the drill string while drilling, so that we can provide the required drilling parameter. Okay, the RPM is important also for the hole cleaning. Why? Because it is make like agitating of the cutting beds, especially in the deviated and horizontal section, and we will describe it with more details later on. And also pipe eccentricity. What is meaning of pipe eccentricity? You know, in the deviated and horizontal section, maybe the pipe tend to go down to the low side. And if this happens, so the hole cleaning will be affected by this pipe eccentricity. To have a good hole cleaning, the pipe should be at the center of the well. But in case we lost this, so the hole cleaning will be affected. Okay, guys, we talk about the annular velocity, and we said that the annular velocity is the most important parameter for the hole cleaning, and we use around 100 feet per minute or higher in the deviated holes. And in the large section, as I said to you, in the top sections, we used the annular velocity will be decreased because of the higher annular volume. So it will be around per minute. So we have to depend on the viscosity, as I said to you. Okay. So guys, this is the equation of the annular velocity. It is the output divided by the annular volume, which is, you know, this number is just conversion number, as I told you in the equation of the pressure. Okay, guys, here we are going to talk about the deviated section. So in this deviated section, in this schematic, we have three parts of the well. When we drill vertical, as I told you, it will not be a big deal. We will maintain our annular velocity. We will maintain our viscosity. We will overcome the slip velocity, and it will be okay. So the whole cleaning will not be that. It will not be an issue. But there is two sections, which is the inclination from 30 to 65 degree, and from 65 to the horizontal 90 degree. Okay, guys, the critical section is the intermediate section. Maybe one of you think that that doesn't make any sense. Why? The most critical section is the intermediate section. This one, I'm talking about this one. Why this one is the most critical? Maybe one of you think that it's the logic that the horizontal section is difficult for hole cleaning than this one. Okay, to describe this section, guys, let's see this small animation. Guys, this is vertical here, and it's going to be deviated. I need you to concentrate on the cutting going down. You see, the cutting is sliding. The cutting is sliding down. I'm trying to lift it up with the drilling fluid, but there is a problem that it is going down, like the cutting on a cliff, and I'm trying to push it up, but in the other side it's going down. And guys, this is called the cutting avalanching. The cutting avalanching here. The cutting has tendency to slide. The cutting itself. Okay, maybe someone of you asked, okay, the cutting here also will go down at the low side of the well. Yes, you are correct. But the problem of the intermediate section is there is something called avalanching, which is causing non-stable cutting bed. At the intermediate section and at the horizontal section, we will have cutting bed. But the difference is that we will have here unstable cutting bed, but we will have here a stable cutting bed. And we can describe it again. Let's see here again. The cutting bed will not be stable. You see, it is avalanching. It has tendency to go down, especially when we stop the pump. All this cutting will go down like the cutting on a cliff. So this is a critical section. And with this section, we try to clean it with multiple high vis sweeps, and also use the RPM and make a lot of circulation before trimming out to make sure that this section is properly clean. Because if we pull out of the hole and we still have some cutting inside this intermediate inclination part of the well, we will have a hole cleaning problem, and maybe we have like hole fill. So we call this effect the avalanching or the tendency, high standing tendency. We call it boycott effect. And the boycott effect is describing how it is a sliding effect, this cutting. Okay, guys. Here in the horizontal section, I told you that we will have a cutting bed, but it will be a stable cutting bed. There is no like this high tendency of sliding, so it will be okay. It will be sliding, but not that much. Okay, so how we are going to deal with the hole cleaning with this horizontal sections? So we use also the pipe rotation, it's important, and we use something called tandem bells. Here, we use the tandem bells. What is the tandem bells, guys? It is combination of low viscosity bell, the same mud or the same mud we are using, but make it low viscosity, followed by high weighted bell. Why, guys? The low viscosity bell is used to make like turbulent flow. It's used to make turbulent flow to make like agitation, extra agitation in the well, so that we can remove this cutting, followed by high weighted bell to help carrying this cutting to avoid to stop it from go down again to the low side of the well. Okay, guys, this is the end of function number 2, which is the hole cleaning. So we will stop for a little for questions. Guys, I think we cover a lot in these 2 functions, and now it's almost 6 o'clock at Egypt, 7 o'clock I think at Lebanon. So I think we have to take the final questions of the session and finalize the session at this point. And maybe later on we make another session or whatever, but we already reached the limit of the allowed time for the session. So okay. Okay, guys. So I will make a quick summary for this session. Guys, we started our session with quick rig familiarization. You know why we did this? Because I get feedback from the organizing guys that most of you are still students, so most of you didn't go to the rig, so we have to make this familiarization. Then we talk about the most important and the most critical function of drilling fluid, which is the pressure control. We talk about the mud window, we talk about the hydrostatic pressure equation, and ECD for pore pressure or formation pressure, fracture pressure. We talk about the factors affecting the hole cleaning. We talk about the hole cleaning in different cleaning sections of the well: vertical, medial, intermediate inclination, and horizontal inclination. So guys, that will be all, and I'm trying to catch up with your questions quickly before giving the mic to my friend Isam. So hole cleaning is much harder in the vertical well? No. Who says this? I said that the hole cleaning, it will be easier it will be easier in the vertical well because it is simple. There is no cutting bed. There is no low side of the well, so it will not be that difficult. I talked to you when we show this slide. I talked to you that this is vertical from 0 to 30. It is a vertical or nearly vertical well. So there is not be issue. Just control your viscosity. Just have good annular velocity. It will not be a problem. I'm talking about the problem or the harder part is from 30 to 35 due to the unstable cutting bed. So it is not harder in the vertical well. Okay. What else, guys? Can you send the recording, please? Okay, this will be from OBA. Okay. Can I see please the formula of annular velocity? Okay, Nizar. Okay, Nizar, this is the formula of annular velocity. It is the pump output barrel per minute divided by the annular space or the annular area, which is the ID of the well, subtracted from the OD of the drill string, and this number is just to convert to barrel per foot. So this will give us barrel per foot, and this barrel per minute, and the final will be foot per minute. Okay, this is the equation of the annular velocity. Okay, BO is the pump output. Okay, and pump output, the pump output will be in barrel per minute. It's like gallon per minute. Okay, ID of the hole, OD of the drill string. Okay, clear now? Okay, guys.
Hello.
Hello.
Guys, are you coming? Engineer Amr, if you have finished, we can finish now.
Asam is talking.
Have you answered the questions? Is there any more other questions?
Just one guy is asking that we need to summarize the slide of the different pressures. Okay, you don't know how to bring. Okay, 100. Okay, just a minute. Okay, you mean this slide, right? Okay, the 1160 or 160 is the 0.465 multiplied by the 4,000 feet. Okay, is that clear? Okay, so the point is, when we find this the pore pressure at this formation, is 1860 psi. Okay, this is a fixed pore pressure. It will not follow the pressure gradient. Why? Because it is enclosed. Because it is enclosed. So when we find this sand lens in shallower depths, it will be a problem. Why? Because it is not following the pore pressure trend. And when I'm calculating my overbalance using the pore pressure trend, so I will fail to maintain the pore pressure or to overbalance the pore pressure in this case. And this is the critical case or the dangerous case. Maybe I have a kick or blowout in this case if I cannot control the well. This is the point of the enclosed formation. Okay, clear? Okay, guys, I'm handing now the mic to my friend Isam. Thank you very much, guys, and I hope I can deliver something important to you or something you make use it.